Very good morning, the third Sunday of January, and thank you for braving the traffic disruption due to the marathon and coming for Chai and Wai or watching it online. Before I introduce the speaker, just to tell you that Chai and Wai happens on the first Sunday of the month at Prithvi Theatre, the third Sunday of the month at Ruparel College. This venue may change later this year. We will let you know if that happens. Of course, we are online on YouTube always. And if a month has a fifth Sunday, we are live from a lab in TIFR. Today, we're going to talk about something which is of great relevance to us, which is energy and harnessing energy from the sun. And to tell us about that is going to be Azizur Rahman. Rahman is a scientific officer at TIFR. He's been there for the last 16 years. He has a master's in energy sciences from Madurai Kamraj University and has been working on various interesting materials that can harvest the sun's energy. And today he's going to tell us about some particular materials. I see you've also got some things to show people. So over to you.
Thank you, Arnav.
Yeah.
Thank you.
For those who are watching it online, please remember the only way we can get your feedback or your questions is if you put in a chat in the YouTube. So please do that, and we will monitor it and request everyone to take those questions. So please put your chats on the YouTube. Okay, over to you.
Thank you, Arnav. Thank you for your kind introduction. I'll first just share the screen.
Yeah. Actually, that some part is missed.
Yeah. Why is it? Okay. Good morning, everyone. Yep.
You're not getting the you're getting a present on it's not coming on the screen either.
Okay.
Get out of present.
Okay.
Get out of present.
No, it's okay. It's fine here, no?
No, but it's what is
Oh, okay.
this.
Oh, okay.
Go ahead.
Okay. Sorry. Yeah. Yeah, it came. Okay. Sorry about that. Good morning, everyone. I am A. Azizur Rahman. I'm a scientific officer at TIFR. I am working. I started my career as a working in semiconductor materials. I first worked in compound semiconductor materials, that is 3 nitrides, and recently I have been working in copper antimony chalcogenides. So today our topic is earth abundant photovoltaics. Photo meaning light, and voltaics is the generation of electricity from the material. Okay, so earth abundant photovoltaic is a very important topic which has a potential to reshape our future. It can give us a clean and sustainable energy for our next generation. So before moving into that, what is the research which drives the research in solar? What is the motivation behind it which drives the research in solar cells? Okay, so the first thing is growing energy demands. Every year there is an increase of 2% of growth in the energy demand by the humans. Okay, and the second thing is we mostly depend on fossil fuels for generating electricity. And the third one is we are polluting the atmosphere, and there are different types of environmental concern. To better understand this, we will see the trends. Okay, so this is a global energy consumption. The humanity in 2024, humanity has consumed something around 175,000 terawatt hour of energy. If you want to compare it, it is like 15,000 million tons of oil equivalent. To get a further intuition, you can say that if you have an oil tanker, which is like 3 tons, and if you have a 20 tankers like that, and you are going to burn that 20 tankers in 1 second, then that much of energy has to be produced. Every second you have to burn this 20 tankers to get the energy for the annual consumption of needs of humanity. So how do you get this energy? There are different methods to produce this energy. The first one is fossil fuels. Okay. The second one is renewable energy, and third one is nuclear. And there are also other small energy production units. The fossil fuels are basically based on the fossils, which are like coal, oil, and natural gas, which are burned to produce electricity. And the renewable energies are like energy from sun, wind, and the heat from the interior of the earth. These types of energy can be used for producing electricity. And there are also, of course, nuclear power plants in which nuclear energy is consumed. So if you see the pie bar chart of what we are consuming, most of the energy is consumed from the fossil fuels. That is around 77% of energy has to be produced from the fossil fuels. We are more dependent on fossil fuels. These fossil fuels create lots of environmental impact, like it produces various gases like SO2, it pollutes the atmosphere, and other main thing is that it can deplete in another 50 to 60 years. On the other hand, the renewable energy resources like solar energy, wind energy, and other types of energy, it doesn't have depletion, and it can give large amount of energy, continuous energy. And nuclear also has some environmental drawbacks, like we have to store this radioactive material, which is very weird. And other 3% are like generating electricity from waste, or using a biofuels or biomass to generate electricity. These type of things are forms the another 3%. Now the problem is fossil fuels may deplete in another 50 to 60 years. So we have to concentrate on producing electricity from renewable energy resources. So moving on, how much energy we get from the sun? If you see, we are getting solar energy that reach our earth around 173,000 terawatt hour of energy. You may be familiar with this number. This is why in 1 hour, the total amount of energy got is something around 173,000 terawatt of energy. This is equal to the average global consumption of humanity per year. Okay, so can we harness this type of energy from the sun? Is there any way to, even a fraction of energy is harnessed, then we will be able to give energy to the whole humanity. So how do you harness this energy? This is we can harness the energy using the sun using a photovoltaic device. Okay, so this is the heart of a photovoltaic device. So you have semiconductors. Basically, you use a semiconductor which can be N-type and P-type, and there will be a junction. When you shine light on this material, you will get energy out of it. This is as simple as that. Okay, so this is the basic mechanism of how a solar cell works. But in order to get a deeper understanding, we will see the types of materials. So the materials can be classified based on their conductivity into 3 types. That is like metals, semiconductors, and into insulators. So what is a metal? So you have bands in the atom. So there will be a conduction valence band in which valence electrons are present, and that is the conduction band. In conductors, these 2 bands overlap each other. So there will be lots of free electrons. So you cannot use this material for solar cell. In other case, there is an insulator in which the band gap is very high. The energy difference between the conduction band and the valence band and the conduction band is very high. You require large amount of energy to make the electrons jump from this conduction band to the valence band. But we have a material called semiconductors, which has a finite band gap, something around, it can vary from 0.5 to 3, 4 electron volt. And it differs. There are wide bandgap semiconductors and other things. So if you have something like this, some semiconductor, then we can make a solar cell devices. So how do you make a solar cell devices? So you need a PN junction. You need both N-type and a P-type material. What is we will take a simple example. For example, if you have a silicon atom have 4 valence electron. So if you dope it with some impurities like a pentavalent thing like phosphor, if you dope it with them, it will combine with the 4 electrons in the outermost shell of the silicon, and then there will be one extra electron in the cell. So this extra electron will act as a make it as a N-type semiconductor material. If you take some trivalent impurity, if you dope this material with some boron kind of material, so there will be 3 electrons and one hole will be created. This type of material is called P-type semiconductors. So what can we do with this material? You combine this material and you form a junction. So this is a PN junction. This is a PN junction. So we have P-type material, we have N-type material. Can you combine this like this? No. You have to make a material in a single crystal, and then so in a P-type material there will be lots of holes, and in N-type material there will be lots of electrons, free electrons in this thing. And there will be a center region which has a depletion, which is known as a depletion region. That is the junction between these 2 regions. Since it is filled with holes and electrons, it will try to create an equilibrium at the center of this junction. So this region is called depletion region. So this makes the solar cell. So when you shine light on this region, for example, so we have P-type material, we have N-type material. When you shine light on this material system, you have a junction, okay, and this is mostly okay. Yeah. So we have a depletion region. Now when light comes into this region, there will be electrons formed in this depletion region, and there will be holes formed in this region. So this will be drifted towards the P junction and the N junction. When there is a drifting, you will get current out of it. So what are the characteristics of the solar cell? So what are the necessary parameters which has to be defined to denote a solar cell? So there are 4 different characteristics like open circuit voltage, short circuit voltage, efficiency, and fill factor. So open circuit voltage, imagine a PN junction, okay, which is open. That is, you measure the voltage between the PN junction. So when light falls on it, there will be electrons. There will be electrons in the P side and holes in the other side. It will create an voltage difference, potential difference in this material. This is called open circuit voltage. And short circuit current. So if you plot this, just want to plot it actually. Okay. Oh. So if you want to understand it correctly, at zero current, when the circuit is open, it will not flow any current. That is, at zero current, you will get a maximum voltage. That is an open circuit voltage. That is VOC. Okay, and then when you connect a load to the circuit, when you short circuit the PN junction, you will get short circuit current. So that is the short circuit current which is shown here. So the efficiency is the maximum power you get. That is P max divided by how much power you are getting out of the solar cell and how much power you are inputting from the sun. So that is P max by P in into 100 will give you the efficiency of the solar cell. And there is a fill factor, which is the squarish region, how much the maximum power is. That will define these are some of the solar cell characteristics of the solar cell. So, okay, we have seen the solar cell, how it works and what are the characteristics of the solar cell. Now we will move on to how you select a material for this photovoltaic cell. So this is the solar cell radiation spectrum of the solar cell radiation. So reaching the earth. So if you can see, it is compared with the ideal black body radiation. If you, the red one is the atmospheric absorption, the red one is the sunlight that reaches at the sea level. So maximum amount of sunlight which comes to the earth is in the region of the x-axis is wavelength and the y-axis is the irradiance, intensity of light reaching the earth. And it starts from something around 400 to 800. That will be maximum amount of energy, maximum amount of solar radiation. It peaks at the 400 to 700, 800 in this region. Okay, so this is the amount of solar radiation which reach the earth. So in solar cells, we cannot use all this energy, and we cannot convert all this energy into the electricity. This is a diagram which shows that if you have a band gap of a material, in the band gap it will absorb the light and it will be used as a electric power. And if the atom is, if the light is below the band gap, so you need some energy to excite an electron from valence band to conduction band. If there is enough energy, it will be converted into electric current. If the energy is below the energy level, it will be wasted. If it is above the energy level, what will happen? It will lose as a thermal energy. So there are different loss factors, and there are only the black region, which is shown in the figure, is the usable electric power which can be used for, which can be harnessed from the solar cell. This is called SQ limit. So the material selection criteria is, first one, we should know what is the ideal band gap of this material. As you can see in this spectrum, the ideal band gap, this is wavelength. Of course, if you convert it to energy, the ideal band gap should be something around 1 electron volt to 1.7 electron volt. In this region, the solar radiation peaks, so we will get maximum amount of output in this region. And you should also look at how earth abundant is it. So availability of the materials, that plays a crucial role. For example, silicon is most earth abundant material. So most of the solar cells are made from silicon. Okay, and it has to be stable. So it should work for longer years. It should be chemically stable. It should be thermally stable. It should not degrade when there is a heat generated in the system, and it should not react with any chemicals. It should be inert to the atmosphere, which it is exposed. And there is also a factor of efficiency. How much efficiency you can create using a given area. That is the efficiency of the cell. The efficiency has to be high. Then you can generate electricity in a smaller area. And you should also consider environmental impact. For example, for making these things, cadmium tellurium cells. Tellurium is the cadmium telluride is somewhat toxic. So you should also consider the environmental impact of the material used in the solar cell while designing the material. And of course, there is a cost factor. When you are generating a solar cell, the cost should be taken into account. It should be cheaper, easily available, and it should give higher efficiency, and it should have an ideal band gap. So these are the factors which decide by which we can select the material for solar cell. Okay, so in the solar cells, so this is a periodic table of a solar cell. So silicon is the material. Silicon and germanium are the semiconductor material, which are elemental semiconductor materials. And then we have other materials in which you form a compound semiconductors, like you combine two materials and you get a semiconductor which is compound semiconductor. And if you take the history of the solar cell material, the first generation solar cell materials are built from silicon. And then there are also materials which are taken from group 3 and group 5. They combined it together. They form gallium arsenide, aluminum gallium arsenide kind of solar cells, which have a band gap of something around 1.5 electron volt, which is ideal for capturing the solar cell. There are also gallium arsenide, indium gallium arsenide phosphide solar cells. and there are indium phosphide solar cells. As we move on, there are also second generation solar. So these are bulk materials. For example, for silicon, a material of silicon, you can pull out a crystal out of it. So in the case of silicon, this silicon or a single crystal, you pull out a single crystal out of it, you make a crystal, and then you cut it, slices, and you make a solar cell devices. Similarly, gallium arsenide is also a single crystal material which can be cut and then you make a solar cell devices. But in the case of second generation solar cell devices, these are like thin films. You deposit this material onto other substrates. For example, copper, indium, selenium kind of things, copper, indium, gallium selenide. These are thin film technology. You deposit this material onto some other substrates and then you make a solar cell out of it. So these are the second generation solar cells. And there are also third generation solar cells, which is a multi-junction. These are like you have a single junction solar cell in which there is one particular defined band gap in only the electrons which are in the band gap region will be observed and you get energy out of it. But in the case of multi-junction solar cell, you will have materials with different band gaps so that you can capture the whole entire region of the solar spectrum. And nowadays, the perovskites, organic solar cells, perovskites are shows the higher efficiency. Nowadays, there are lots of research going on perovskites, and there are also dye-synthesized solar cells which have been used. So the take-home message is there are different kinds of material which can be used. You combine this material and you can form a solar cell with optimum band gap. Okay, this is the solar cell efficiency graph which will be released by this National Renewable Energy Laboratory. So this records the efficiency, lab grade efficiency, which has been reported. So for example, if you see silicon is the blue one. So if you see the silicon started something around 1976 or 77, and still research is going on, and we have reached up to an efficiency of 28% of efficiency. And you can also see there are other materials like copper, indium, indium, gallium selenide, and other materials, which still research is going on and they're trying to improve the efficiency of this material. Other than this, which started earlier, there are some materials which are emerging right now. That is the dye-synthesized solar cells, the perovskites. All these materials has been analyzed after 2000 or something. So perovskites has reached an efficiency of around 30%, and other solar cells still research is going on to improve the efficiency of this material. So our main topic is earth abundant solar cells. So if you see the abundancy of elements. Yeah, sure. So no, it's okay. I can speak louder. Yeah. So if you can see, this is the silicon is the earth abundant material. It's okay. You can keep some fans. Okay. So if this is a chart showing the earth abundance of the material elements that can be used. For example, there is silicon, copper. These are the abundant materials. How much abundancy is there regarding the particular element? Okay. So for example, silicon is the most earth abundant material. If you see, there are copper, zinc, gallium, aluminum, antimony, all these materials. This shows the abundancy of these elements in the earth. Okay. If you can see, silicon is the most earth abundant material, and it is the well established technology. So what is the problem with silicon? Why you are doing earth abundant materials again? So that we will address. There are some problems with silicon. The first problem is it is an indirect band gap material. As I already told you, it has a band gap of 1.1 electron volt. Okay, and indirect band gap meaning the valence and conduction band, it will be shifted. The valence and conduction band will be shifted. You will have an energy gap, but you need some more energy to reach the conduction band. So the energy will be wasted in the form of heat. So in order to do this, we require a thicker layers, and there is also a SQ limit of this material. You can maximum theoretically you can reach only 29% using the silicon solar cells. More than that, producing silicon is very hectic process. You have to purify the materials. You find abundant of silicon on the earth, but you have to purify the silicon. You need pure silicon for making this solar cell, and you have to. It's an energy-intensive production, so you need lots of energy to produce a solar cell. That's why the installation cost is very high, and also there is a material loss. When you make a solar cell, you have to cut the slices, and there will be 50% of materials is lost during this production of the solar cell. So there are some of the, these are the problems with the silicon. So we have to push our research into other earth abundant materials which can be used. There are lots of research going on. For example, CZTS, that is copper, zinc, tin, sulfur or selenoid. These are the new materials which are earth abundant, and it can also be used as a material. It has a direct band gap. The band gap ranges from 1 electron volt to 1.5 electron volt. It have a very high absorption coefficient. Similarly, there are material copper antimony sulfide, and there are many materials which are coming out recently. Research are going on this in this material systems. So the material I have been working on is copper antimony sulfide, CAS material system. Copper, antimony and sulfur are earth abundant. So we wanted to explore whether this can be used as a solar cell material. So what is copper antimony sulfide? So copper and antimony, you combine copper, antimony with the chalcogenide materials. That is, what are the chalcogenides? The chalcogenide is sulfur, and then selenium, and then tellurium. So when you combine this material, we get different materials with different stoichiometric ratio. We will define it. So advantage of using this material is these materials are earth abundant, they are low toxic, they have a tunable band gap, they have a very high absorption coefficient, and more than that, they are intrinsically p-type material, which can be used. Okay, so it has a wide range of alloys ranging from Cu-Sb-2, Cu-Sb-Se2. It has many alloys. For example, if you see one of the element, copper, antimony, sulfur, we will take one as an example. So copper, antimony, sulfur, as I already told you, it has a high optimum band gap. It is used in various applications. For example, research is going on for improving the efficiency in as a photovoltaic material. It has also a high thermoelectric performance. So people are researching in treating it as a thermoelectric material. They are also layered structure. That is, you can peel off this material and you can have a layered structure in this material. So people are using it for supercapacitors, that kind of a research. So my material of interest, I have selected 3 materials, which is copper, antimony, Cu3Sbs4, Cu3Sbse4, and Cu-Sb-2, Te2. So the challenges in growing this material is these are very low temperature synthesis material. For example, this is a phase diagram of this material. You can see even at 300 degrees Celsius, if you change slightly the composition of the material, you can change the stoichiometry of that material. For example, you can create Cu3Sbs4, you can create Cu2, even at a temperature of 300 degrees Celsius, you can create all this material by changing the initial composition. Another problem is phase purity. If you make this material, there will be some kind of secondary phases or ternary phases which will always exist. So we have to avoid these kind of purity issues. You have to make a phase pure material, and you have to avoid secondary and ternary phases. So we were trying to, in my research, I was trying to synthesize this material, phase pure, by optimizing different parameters. Okay, for example, so in copper antimony sulfides, there are 4 stable phases. There are more phases, but these 4 phases are very stable. Okay, so the first one is Cu-Sb-S2, Sb3. They are at different stoichiometry ratio. The interesting thing is that it has different crystal structure. It has different electrical and optical properties. For example, Cu-Sb-S2 has orthorhombic and it is 1.5 electron volt, and this is tetragonal and 0.9 electron. So you have a range of band gaps, and you have different physical and chemical properties of this material. So how do we synthesize a single material, and what can we do about this? So these two materials we were interested in, and we tried to synthesize this material. So while growing this material, you have to take into, there are many challenges involved in growing this material. For example, first one, growth part. You have to get the obtaining the desired composition. You have to change the temperature. You have to play with lots of parameters, and you have to get a material which is phase pure. You don't have any secondary or ternary phases, and you should avoid all these things. And characterization, you should know what the material you have grown is actually what you have grown. So you will characterize using different characterization techniques, and then from the feedback of the characterization technique, you will optimize the different parameters. Okay. So let us take, we will just check the one example of Cu-Sb-4. So how did I grow this material? First, I have taken a sapphire substrate. It's a two-step process in which I have taken sapphire as a substrate, and then I have used co-sputtering. So we need two metals, that is copper and antimony. The copper and antimony are deposited using a co-sputtering process. So you have a chamber in which we have a metal targets. You have an ionizing gas, and we do it with a sputtering process, physical vapor deposition sputtering process. And we maintain uniform temperature and pressure. We maintain the uniformity by changing different parameters. And once you deposit this copper and antimony metal, we will move on, and we will seal it in a quartz ampule. For example, this is a quartz ampule which we use. So this is a, if you can see it, this is a deposited thin film. This is deposited with copper and antimony, and these are some tellurium crystals. So we seal it in a vacuum atmosphere using a diffusion pump. Using a diffusion pump, we go up to a pressure of 10 to the power of -6 to remove all the impurities, all the oxygen contamination and other things. We grow at a very low pressure. More than that, you raise the vapor pressure of the tellurium so that it gets reacted with the metal precursors. We do this quartz sealing using a vacuum sealing process. This is the diffusion pump we use, and we seal this tube under vacuum. After that, we used a single zone tubular heater furnace to heat this material. So these materials can be grown at a temperature of 400 degrees Celsius. At a temperature of 400 degrees Celsius, these will react together, and it will form copper antimony sulfide or selenide. And after that, we do different characterization. We do structural and optical characterization, for example, XRD, X-ray diffraction, SEM, Raman, and other things. And from the feedback of this material, we repeat this process to get a phase pure Cu-Sb-4. So this is the schematic representation of a two-step growth. You have copper and antimony metal, which will be deposited onto the substrate. By changing the RF power supply, you can change the composition of the copper and antimony, and then you seal it in a quartz ampule. When we rise the temperature, this sulfur, selenium will diffuse into your copper and antimony metal, and it will form the desired stoichiometric CAS material system. So once we design the growth parameters, we have to play with the different parameters. For example, at what temperature you keep this material system to have a phase pure material, and what is the copper and antimony ratio, how much time you have to keep this keep, and what is the sputtering temperature, what is the sputtering pressure. There are different types of parameters. So we change these parameters one by one, and then we get a feedback from the characterization techniques, and again we try to optimize this material. For example, this is the XRD curve. So in this thing, we have studied the influence of temperature on the growth of this Cu-Sb-4 material system. So we have raised the temperature from 200 degrees Celsius to 450 degrees Celsius. So 450 degrees Celsius, as you can see, at lower temperatures, you can see many secondary phases. So these are the inverted triangles and circles are like elemental copper, elemental unreacted antimony, unreacted sulfur, and there are different types of impurities present if you grow below 400 degrees Celsius. If you grow above 400 degrees Celsius, you get a cleaner phase pure Cu3Sb4 thin films. So as you can see, the higher temperature gives you the phase pure copper antimony sulfide materials. At a lower temperature, you have impurity phases like antimony sulfide, copper sulfide. There are binary and ternary phases which appear at the lower temperature. So higher growth temperature gives a better crystallinity. Similarly, we have done the Raman spectroscopy in order to correlate with the structural things. Raman spectroscopy is nothing but you do the vibrational properties of this material. You put a laser light on it and you measure the scattered radiation. You measure how much it is shifted. So that will give you the signature of the what you have grown. So, for example, this is a Raman spectra grown at different temperature. For higher temperature, you get the Raman signal corresponding to Cu3Sb4, and at lower temperature, that is around 300 to 200 degrees Celsius, you can see the impurity phases like unreacted antimony is present in this material, and there are CUS peak is present in this material, and there are secondary phases which arise due to the poor thermodynamic conditions. So we will also see the surface morphology of this thing. So for example, if you can see at 200 degrees Celsius, you get a vertical flake-like growths. These are basically CUS copper sulfide crystals. And if you see at 425 degrees Celsius, you get somewhat coalesced layer, which is fully covered the material and which can be used for solar cell materials. In this thing, the crystalline size is very small, and here we can see the void. So we decided that 425 is the optimum temperature for growing this type of material. So you can see voids in between which should be avoided. This 425. We want a full coverage and more crystallite size. We want a conformal coverage. So we have also studied the optical properties of this material. So using transmission and reflectance spectra, we can clearly see that there is a band gap. So these are the band gap of this material. It has a band offset something around 1.3 to 1.5, which corresponds to copper antimony sulfide, and that's why we can use it for solar cell applications. And there are also sub-band gap absorption, which is because of the impurity present in this material system. No, it's okay. No, one is transmission and one is reflectance. This is reflectance, this is transmission, that is reflectance. So at lower temperature, we get maximum amount of antimony sulfide impurity phases in this thing. So we further did other structural characterization like high resolution TEM imaging, and for example, we have seen how the atoms are aligned, and we have done a TEM imaging of this thing. So finally, we have changed different parameters. This is a influence of if you change what happens if you change copper and antimony ratio, and that we have also studied what happens if you increase the chalcogenation time. So you can see that from this, what I want to say is we have optimized the different parameters, and we try to grow a phase pure material. After getting the phase pure material, what we can do, we have demonstrated a solar cell. So in this thing, we have used copper antimony sulfide as a material system, and then we have the copper antimony is intrinsically p-type material, and we have used n-type gallium nitride. So gallium nitride is grown using a MOB reactor, and then we try to measure what is the efficiency of the solar cell. The efficiency is something around 0.5%, which is very low as a starting material. But why is that gallium nitride? No, this is intrinsically p-type material. You need an p-type material, Cu3Sb4, and we took a n-type gallium nitride material. So we wanted to make and we have demonstrated an efficiency of 0.5%, which is until now this material has an efficiency of 0.5. There are other stable phases of this material which have given something around 3.2% of efficiency. So the research has been started right now, and people are exploring how to improve the efficiency of this material. So beyond this, we have also studied beyond photovoltaics, what this material can be used, how this material can be used. So we have observed a weird phenomena in which if you shine light, if you shine an intense laser light onto the substrate on this copper antimony sulfate material, we see some marks, and there is a laser heating or something is happening in the substrate. So when we were doing our Raman measurements, we found that if you have a high intense laser, if you increase the power of the laser, the material is transforming into something else. We wanted to analyze this, what is happening in the material using the Raman spectroscopy itself. So we use green laser, and we use a 30 milliwatt amount of laser, and it damages the surface. This is the SEM image of the copper antimony sulfate, and even in optical image, you can see that the surface morphology is changing. So we wanted to deeply investigate what we can do with this type of phase transformation. So we have systematically investigated this phase transformation using Raman spectroscopy. So this type of phase transformation has been previously reported in different substrates like copper sulfide and antimony sulfide kind of things, but it has not until now reported for this copper antimony sulfide. So as a first step, what we did is we made a phase view Cu-Sb-Chalcogenides material. We checked all the properties, for example, the XRD image, and we got feedback from the different characterization techniques, and we found the optimized temperature, optimized condition for growing this material. So after the growth of the material, we have phase pure material. Then we started doing laser power dependent Raman spectroscopy. For example, at a laser power of 0.7 milliwatt, at a very low power, you can see copper antimony sulfide peaks, okay, which is the characteristic of copper Cu3Sb4. Once you increase the power, these peaks shifts, and we can see that there is a change in the spectrum. Okay, so even at 1.5 milliwatt, the peak has been shifted from here to here. Okay, this is 333, this is 317 centimeter inverse. As you put the light, the intensity is clear. This thing is getting clear, and after some time, this further degrades and it forms some other phase. You get a peak of some other phase. So basically, what we are doing is we are changing the laser power from 0.7 to 20 milliwatt, and we have recorded the spectral changes. What is happening? So in the initial phase, at the low power, you get copper antimony sulfide, that is ferritinite phase, and when you increase the laser power, we get Cu3Sb2. It is a different stoichiometry, stable phase of copper antimony sulfide. So this is Cu3Sb4. There is a phase transition after 1.5 milliwatt power, and these peaks correspond to Cu-Sb2, and finally it transformed into Cu2, yes, copper sulfate. So the phase transition happening from Cu3Sb4 to Cu-Sb2, and then finally it degrades into Cu2S. So this can be imagined using a Raman mapping of the Raman spectra of this material. So we have intentionally irradiated a small region using a high laser power. So something around 5 milliwatt or 10 milliwatt of laser power, and we did a Raman mapping. So this corresponds to the Raman mapping of two different phases, that is Cu3. So we have irradiated the region, and then we probed it with a low power, so 0.7 milliwatt, so that we don't make further damage. When we plotted it, we see that the center region is Cu3, the peripheral region is Cu3Sb4, which is not exposed to the laser. The exposed layer is Cu-Sb2. So we can clearly differentiate, and this process is irreversible. So once you shine a light on it, it will absorb the energy and it will it is getting transformed into another phase. So Raman mapping, so we have it. Sorry. So we have irradiated the region and we have found that there is phase transformation happening in this material system, and this system, this process is irreversible. So we wanted to determine how much temperature we need to carry out this phase transition. So for that we have used a computational COMSOL software to simulate how much temperature we get when we shine laser on it. So we established a simple model and we have solved the heat equation, and we have seen that. So this is the temperature accumulation as a function of a time. So at 0.7 milliwatt, the temperature is something around 300. The temperature is something around below 350 K. When you rise the temperature at even at the phase transition temperature, it reaches a temperature of 460 K. At this temperature, the phase transition is happening. So if you plot it, the center, since the laser beam is a Gaussian beam, we see that the center point is at highest temperature and it degrades. The highest temperature is something around 460 degrees Celsius, by which we have calculated the optimum temperature required to do a phase transition. So further, we have done tried to observe what is the kinetics of this phase transition happening in this material. For example, so as I earlier showed you, this is a power dependent Raman spectroscopy in which lower power gives you Cu-Sb-Sbs4. At higher power, you get a phase transition and you will get Cu-Sbs2. At much higher power, you will get Cu2s. But so this is the thing. And we have done the Raman mapping and we have done a line scan of this material. So we have done an elemental mapping. So this is, we have irradiated with different laser power. For example, this is 15 milliwatt, this is 12 milliwatt, 9 milliwatt and 6 milliwatt with different laser power. You can see that there is a change in the diameter of the irradiated region also. We have plotted with elemental composition of this material, corresponding different elements present in this material, how it is getting evaporated. So you can see sulfur is the easily melting material, it gets evaporated, and then there is antimony. So you can see the line graph. So in the laser irradiated region, there is a material loss which is going on. So these materials get evaporated and it tries to form a different phase. So we have also done a TEM imaging. We saw that we have irradiated this region. Okay, we have taken these flakes in a TEM grid and we have given laser power of something around 5 milliwatt of laser power. When we can clearly see there are three different regions. Okay, so one is Cu2s, which is a high intense, and second one is Cu-Sbs2 and Cu3-Sbs4. So in order to check what is happening here, we have done the electron diffraction pattern, and we have seen that this material can, of course, this material is Cus2 and Cu-Sbs2 and Cu3-Sbs4. And further, we did time-dependent Raman spectroscopy, and we have determined how much. So, what is the rate constant of this? We have determined how much energy is required to initiate this phase transition process. So, what we have done is we have done time-dependent Raman spectroscopy. So, for example, at initial phase, even if you shine light, for example, this is 0.5 milliwatt. Even if you shine this light up to 1000 seconds or 20 minutes, there will be no change in the material system. For 0.7 milliwatt also, there is no change in the material system. If you go for a higher pressure, you can see that this is the Cu3-Sbs4 peak. And after some time, the material gets degraded, its phase transformation is happening. At something around 5 minutes, the material gets transformed into another material. And it is quicker if you increase the laser power. This is 1 milliwatt, 1.5 milliwatt, and for 3 milliwatt, it happens instantaneously. So at much higher power, that is 12 milliwatt, we can only see the copper sulfate peak, which is dominating. So with this, we have calculated how much energy is required. The activation energy for transforming this material from Cu3-Sbs4 to Cu-Sbs2 is something around 12.2 2 kilojoule of energy. So similarly, we have done copper antimony like copper antimony sulfide. We have also done copper antimony selenide and copper antimony telluride material system. So we have compared the growth of this material. So we have used, we have deposited with the same thing. We have deposited copper and antimony metal, and then we have put tellurium or selenium or sulfur in the quartz ampule, and we have synthesized and found the optimum condition for growing copper antimony sulfide, selenide, and telluride material system. And yeah, so we have done the structural and optical characterization of this material, and we have made this material. So in summary, what we have done is we have synthesized copper antimony sulfide. We tried to optimize different parameters. We have grown this material using two-stage growth process. We have optimized different conditions, and we got a phase Q Cu-Sb-Chalcogenides material. With this material, we have demonstrated that this material can be used for solar cell applications, and we have also found that this material can be transformed from one phase to another phase by shining laser onto it. When you are shining laser onto it, it can be transformed from Cu3Sbs4 to Cu-Sb-2, and it can be used for different applications like data storage, or you can use it for many applications like holograms and other things. And you can also create heterojunction, lateral kind of heterojunctions. So yeah, so we have made this material.
Okay, thank you. You are studying engineers, which is an ideal candidate for photovoltaics in future? Telluride or selenium?
No, sulfur.
Oh.
Sulfur. Cu-Sb-2. The thing is that if you have selenium and tellurium, and you have a unified method, you can change the composition of this material, and you can change the band gap of, I think you can tune the band gap of this material system. Yes, sir. There are works, but laser-induced phase transition kind of work this is the first time we have reported this kind of thing. Which one? Correct. No. There is no reports on laser-induced phase transition. Yes, sir. Yeah.
Overall, what is the future of solar energy?
What is the future of solar energy? Yeah, we can. I mean, right now it is around 5.5% of the. We can create something around 5.5% of total solar energy in the sector of renewable energy. But we can increase, if we can increase the efficiency of the material, and if we can play with the parameters, then of course we can. We have to combine all the renewable energy resources, then we will get a good efficiency.
So since the toxicity of this material is less,
yeah.
Also because of the appetence, maybe whenever it comes up as a commercial venture, the capital input would be much less in this kind of things. Also, the toxicity will reduce.
Reduced, correct.
Efficiency for
unit cost is different because this is a direct band gap material. We require much less thickness, and this is a thin film. You don't require a. Might be a future candidate. Yes, sir.
Just one second. Let me stop this. Okay, yes. Just one second. So for the online audience, thank you for watching. Thanks, Rahman, for this thing. Just remember that 2 weeks from now, the first Sunday of February, we will be at the theater. Most likely on Sushil will speak on some quantum communication-based ideas. That's coming up next. And keep watching online if you cannot meet in person. On that note, thanks again, and let me just stop this live stream, and then we go ahead. Yeah.